The sonar operator's hand freezes over the intercom button. Above the submarine, 3 meters of Arctic ice. Below, missiles carrying enough firepower to devastate dozens of American cities. And now, in the command post, a reading that shouldn't exist. The oxygen scrubbers are failing. The captain has hours of breathable air, no Polynyas, those life-saving holes in the ice, within range. The diesel generators can't recharge batteries under solid pack ice without killing everyone aboard. But here's what Moscow never told him. His boat was always meant to stay under. For 3 decades, Delta-class submarines played a game where the rules guaranteed suffocation. They carried missiles with 8,300-kilometer range, far enough to hit New York from under polar ice. But the noise from surfacing would expose them to American attack subs hunting in the dark. Stay hidden and run out of air. Surface and die anyway. The Americans knew these submarines were under the ice. What they never understood was why the Soviets kept sending crews who couldn't come back up, and what those missiles were actually waiting for. Earlier that December morning in 1984, a Delta-class submarine backed away from the pier at Gadzhiyevo Naval Base on the Kola Peninsula. She was one of several Delta boats assigned to Northern Fleet Bastion Patrol in the Barents Sea. Mission duration? 90 days submerged. Mission goal? Maintain second strike capability. The promise that if America launched first, enough Soviet missiles would survive to burn every major city on the eastern seaboard. The boat's commanding officer signed the patrol orders and passed them to his executive officer. The crew sealed the hatches, the reactor went critical, and the submarine slipped beneath the gray water into a world where the sun would remain below the horizon for weeks. 2 days later, the captain ordered depth 120 meters beneath the ice pack, speed 4 knots to minimize flow noise. The reactor ran at reduced power, enough to keep the boat moving and the lights on, while maintaining acoustic stealth. Periodically, the ice profiler sonar sent a pulse upward, measuring the distance to the frozen ceiling and searching for Polynyas, the rare open water gaps where a submarine could surface if orders came. The crew moved through their routines in near silence. In the sonar shack, the operator logged ice thickness, 2.1 meters overhead. Within safe surfacing margin. No contacts. No surface traffic. No reason to run the emergency diesels yet. In the missile compartment, 16 R-29R rockets stood in vertical tubes, each one over 14 meters tall and weighing 35 tons. The missiles carried multiple 200-kiloton warheads, typically 3 or 7 per rocket, programmed before departure for American cities whose names the crew never spoke aloud. Pre-programmed targeting data was stored within the guidance computers, waiting for a launch authorization code that might never come. The patrol zone covered a vast area of the designated bastion, a rectangle of ocean the boat would never leave. Soviet doctrine was explicit. Delta boats would not roam the Atlantic like the older Yankees. They would hide under Arctic ice, where they were significantly harder for American attack subs to track. And they would wait. Northern Fleet doctrine called it a bastion, a protected zone where Delta submarines could launch missiles without ever exposing themselves to open ocean. A screen of Victor III and Akula-class attack submarines, typically a dozen or more vessels during heightened alert, patrolled the perimeter, hunting for American intruders. Surface ships and maritime patrol aircraft added layers of detection. The idea was simple: sacrifice mobility for survivability. The Soviets accepted they could not match American submarine quieting technology, so they stopped trying to hide in the Atlantic, and instead turned the Barents Sea into a fortress. Captain Grishkov's job was not to hunt. It was to stay alive long enough to launch if the order came. 3 under the ice. The sonar operator's voice cuts through the control room. Ice thickness, 1.8 to 2.5 meters. Safe margins, for now. No contacts, no acoustic activity. But in these waters, silence isn't comfort. It's a question mark. The executive officer runs his drills like clockwork. Missile tube flood checks, launch authorization code rehearsals, emergency surfacing procedures, each one a reminder of what this boat carries. The crew rotates through watches, eyes fixed on screens that show nothing, listening for sounds that don't come. In the galley, cooks ration the fresh vegetables, 3 weeks until they're gone. Then it's canned stores for the rest of the patrol, months of tin and preservatives. Every morning, the captain reviews the same standing orders: maintain stealth, remain under ice, monitor VLF traffic continuously. The routine is deliberate, boring by design, because boring means the deterrent is working. Boring means the world above isn't tearing itself apart. But 7 days in, that word, boring, starts to feel different. Not like safety, like waiting. But the ice pack was never static. Ocean currents and wind shear pushed it 5 to 10 kilometers per day, turning yesterday's clear Polynya into today's 4-meter pressure ridge. The ice profiler sonar gave bearing and rough thickness, but no real-time map of horizontal structure. It could tell the captain how far away the ice was, but not whether a ridge was drifting toward him or whether the patch of thin ice he planned to surface through would still be there in an hour. Weather data from the surface could predict drift, but K279 had none. The boat was blind to everything, except the snapshot directly overhead. Communication with Moscow came through a trailing wire antenna, a thin cable spooled out behind the boat at 50 meters depth. It received very low-frequency radio, the only signal that could penetrate ice and seawater. VLF operated at 20 to 30 kilohertz, a wavelength measured in kilometers, and it carried data at 100 bits per second, slower than a 1960s telephone modem. A full launch authorization package reportedly contained around 12,000 bits of data, encrypted targeting updates, authentication codes, time on target. 12 minutes to receive, 3 more minutes to decode and verify. During that entire window, the boat had to maintain depth, course, and antenna alignment. Any maneuvering would break the link and force the transmission to restart. The nuclear reactor provided propulsion and hotel power, but if it failed, or the captain needed rapid battery recharge, the boat carried emergency diesel generators in the aft compartment. Those diesels were insurance against reactor shutdown. They were also a death sentence. Running diesels underwater meant snorkeling, raising a mast to pull in air and vent exhaust. The diesels themselves radiated 140 decibels at 180 hertz, a low-frequency roar that propagated through Arctic water with almost no absorption. American attack subs could detect that signature at 40 kilometers or more. Running the diesels meant telling every U.S. boat within a 100-kilometer radius exactly where you were. A Delta-class commander would have reviewed the standing orders again around day 12 of the patrol. Maintain stealth, no active sonar, minimal reactor noise, no diesels unless survival depends on it. Remain under ice. The ceiling is your shield. Monitor VLF traffic continuously. The launch order might arrive with no warning. If a valid launch authorization is received, the boat must surface through a Polynya within roughly 20 minutes, the estimated window before American counterstrike capability could neutralize the threat. 20 minutes to find thin ice, maneuver into position, verify no overhead obstructions, blow ballast, and break through. Miss that window and the entire patrol becomes irrelevant. The missiles stay in their tubes while America destroys the motherland. Soviet doctrine laid out the dilemma in stark terms. Run diesels during a reactor casualty and risk detection, or rely on the reactor's automatic systems and accept the vulnerability of any emergency ascent. Either choice could doom the boat. If the reactor scrammed and backup systems failed, the boat would lose propulsion and sink below crush depth. If emergency diesels were heard, tactical doctrine assumed a U.S. torpedo could arrive before missile launch procedures were complete. Soviet submarine designers understood these risks. Northern Fleet commanders planned around them. And every Delta captain accepted the calculus, because the alternative, trying to outquiet American submarines in the open Atlantic, had already failed during the Yankee patrols of the 1970s, when U.S. attack subs trailed Soviet boomers 90% of the time. In a scenario that could have unfolded on any high-readiness patrol, perhaps around day 31 at sea, the VLF receiver chimed in the Radio Shack. The communications officer tore the printer tape and read the header. Priority message, combat alert, missile launch readiness required. Not a drill code, not a routine status check, a real alert. But the full authorization code had not yet arrived. Soviet communication protocols of the era required significant time for slow-frequency transmission and multi-stage authentication. The communications officer activated the intercom. A commander, such as the noted Soviet submariner Igor Grishkov, would have acknowledged and ordered battle stations. The executive officer began the pre-launch checklist. The missile technicians powered up the guidance computers, and the clock started. The sonar operator's voice cut through the tension. Ice thickness increasing, 3.2 meters overhead. Pressure ridge drifting across the patrol box. No Polynya within 8 kilometers. Captain Grishkov checked the ice profiler display himself. The thin patch they had marked yesterday was gone, buried under a ridge that had rotated in from the northwest. The boat was too deep to surface safely through ice that thick. Punching through 3 meters of multi-year ice would crush the sail, flood the bridge trunk, and compromise the hull. They had to move. Now. The captain ordered a course change to bearing 310 toward the last known Polynya coordinates logged 3 hours earlier. Speed increased to 6 knots. The reactor hummed at minimal load, just enough to maintain steerage in critical systems. Battery reserves held steady on standby. The crew felt the subtle increase in engine noise, the faint hum transmitted through the hull. In the sonar shack, the operator adjusted filters to compensate for on-ship noise. The VLF antenna remained deployed, still downloading the launch authorization message. Several minutes remaining. The communications officer confirmed the link was stable. For now. According to reconstructed accounts of the encounter, passive sonar detected a high-frequency active ping. In this tactical scenario, bearing 042, range estimated 18 kilometers. The sonar operator replayed the signature on the waterfall display. Frequency analysis matched a U.S. Los Angeles-class attack submarine, the most advanced hunter in the American fleet. Inside the Bastion perimeter. The executive officer cross-checked the contact against known positions of friendly Victor-class boats. No match. The American had slipped through the screen. The Delta's commander faced a critical decision. The U.S. boat was between K-279 and the Polynya. The tactical picture was clear and terrible. According to dramatized accounts of Soviet missile drills, the submarine needed to reach the Polynya within minutes to surface before the launch window closed. The U.S. submarine was blocking the direct route. The captain faced an impossible choice. If he increased reactor output for high-speed evasive maneuvers, the increased pump noise would give the American boat a firing solution within minutes. If he maintained silent running at minimal reactor power to avoid detection, he risked insufficient speed to reach the surfacing zone in time, leaving no margin for emergency maneuvers if the U.S. boat fired. Either way, the American had the advantage, and the clock was still running. The captain stared at the sonar display. Every 30 seconds, a new reading, a snapshot of the ice directly overhead, and nothing else. The ice profiler couldn't see what mattered most, the horizontal structure. Pressure ridges extending sideways from the main ice mass? Invisible. Drift direction without surface weather data? Impossible to predict. The submarine didn't have that data. 3 kilometers ahead, the ice conditions were nothing more than a guess. The sonar used an upward-looking 30 kilohertz beam, measuring round-trip time to the ice underside. Sound traveled at roughly 1,450 meters per second in Arctic water, giving them a resolution of plus or minus 0.3 meters in ice thickness. Precise, yes, but precision meant nothing when you couldn't see what was coming. They had a snapshot, not a map. The ice above them had to be less than 2 meters thick, thin enough to break through. No ridges within 50 meters of the sail, The Delta III sail jutted 8 meters up from the hull, a tower of steel that would punch through first. But what if the ice was too thick? The captain knew the math. Multi-year ice could exert crushing forces. Calculations suggested impacts exceeding 200 tons per square meter. That force would crush the bridge trunk, the reinforced cylinder connecting the sail to the boat's interior. Around him, the hull groaned under depth pressure. 120 meters down. If that trunk crumpled, seawater would flood in. They'd lose the forward escape hatch. Watertight integrity, gone. Everyone forward of the reactor compartment would die. The American sub was still closing. Safe surfacing required ice thickness under 2 meters. Standard procedure called for all masts to be retracted. The reinforced sail itself, not the delicate periscope, would take the impact. That 8-meter tower would punch upward through the ice. If they got it wrong, if the ice was thicker than their instruments said, the bridge trunk would fail. Flooding meant death at this depth. No time for a second attempt. The launch code was downloading. 12,000 bits crawling through the ice at 100 bits per second. 2 minutes if everything went perfectly. But nothing was perfect under the Arctic ice. Signal fading. Multipath reflections bouncing off ice ridges and thermoclines. The effective rate kept dropping. 80 bits per second, 70, 60. What should have taken 2 minutes was stretching toward 5, then 10. Error correction protocols kicked in, adding overhead, pushing the window to 12 minutes. 15 if the ice got any thicker. 15 minutes at antenna depth. 15 minutes holding course in a straight line. 15 minutes while an American attack submarine closed the distance, listening for exactly this. A Soviet boat forced to stay shallow, stay slow, stay predictable. The code was at 40%, then 50. Every additional minute increased the probability of detection. Every second the download continued was another second they couldn't maneuver, couldn't dive, couldn't run. What if the missile's guidance system was so precise it could hit a target 8,300 kilometers away? It couldn't. The R-29R used stellar inertial guidance, gyroscopes tracking orientation during boost, a star tracker updating position mid-course. But gyroscope drift, estimated at around 0.15 degrees per hour in systems of this generation, was small. Cumulative over 30 minutes, fatal to accuracy. Circular error probable, the radius where 50% of warheads land. It started at 500 meters for short-range shots. At maximum range, 900 to 1,200 meters. Fire from protected Arctic waters at targets deep in the continental United States, over 8,000 kilometers away. And you had a 50-50 chance of landing within 1 kilometer of your aim point. Acceptable for destroying a city, useless against a hardened missile silo. That was the trade-off. Range bought the submarine's safety from retaliation, but accuracy suffered. And right now, with a US torpedo closing in, range meant nothing if they didn't survive to fire. The sonar operator's hand trembled over the diesel startup switch. He knew what the numbers meant. 140 decibels RE 1 micropascal at 1 meter. Low-frequency energy that would slice through the isothermal Arctic water at 1,450 meters per second. No thermocline to hide behind, nothing to absorb that acoustic signature. And the Americans? Their passive sonar was built for exactly this, optimized for low-frequency tonals. Depending on ice noise and their own masking, any US attack sub within detection range would pick up the signature. Every SSN that heard it would start closing. The only question, could they prosecute the contact before the submarine went silent again? He pressed the switch. The Northern Fleet Bastion, 1.4 million square kilometers of frozen hell. Operational records suggest roughly a dozen Victor III and Akula-class attack submarines prowling the perimeter, each boat covering roughly 115,000 square kilometers. Do the math. Any American attack sub punching through that screen? War games and simulations from the era suggested better than 60% odds of reaching firing position on a delta before detection. Soviet strategists knew those odds. They hated them. But the alternative was worse. Trying to defend delta boats in open ocean meant certain death. Under the ice, the deltas at least had a chance. In the Atlantic, they had none. The math was unforgiving, and everyone knew it. 0857 hours. VLF code download, 60% complete, 6 minutes remaining. Battery charge at 68%, sufficient for 30 minutes at current speed. But if the boat had to sprint or dive deeper to evade torpedoes, reserves would drop to approximately 12 minutes of high-power maneuvering. The executive officer ran the numbers again and confirmed them to the captain. 12 minutes. Likely not enough time to reach the Polynya, surface for antenna deployment, authenticate the launch code, and spin up the missiles. The boat was already committed. There was no turning back. In reconstructed accounts of tactical encounters like this, sonar operators would track contacts with precision. Bearing, range, closure rate. According to available records, U.S. submarines typically relied on passive sonar for stealth during tracking missions, though active sonar pulses were occasionally used as signals of detection. The pursuing boat had likely acquired K-279 on passive tracking, but had not yet committed to a firing solution. The reasoning was tactical. American commanders needed to confirm target classification before launching Mark 48 torpedoes, because a mistake, sinking a friendly or neutral vessel, would trigger an international incident. That caution, when it applied, bought pursued submarines a few more minutes, but only a few. The captain ordered what submariners call a silent sprint. Reactor power increased, speed building toward 9 knots, heading for the Polynya estimated at 6 kilometers ahead. No diesels. He was accepting battery drain and gambling that ice thickness would decrease before the American sub closed to firing range. The helmsman acknowledged and advanced the throttle. The boat surged forward. In the engine room, the reactor control officer watched coolant temperatures climb. The noise was unavoidable. Flow noise over the hull increased dramatically with velocity, but it was still quieter than diesels. Quieter meant a chance. The profiler showed thickness dropping to 2.6 meters, still above the safe margin, but trending down. The executive officer calculated 4 more minutes to reach the Polynya if current speed held. But the VLF code would expire 18 minutes after full download, leaving only a 6-minute surfacing window once they arrived. 6 minutes to verify no overhead obstructions, blow ballast, break through the ice, extend radio masts, and authenticate the code. There was no margin for error. If the ice was thicker than the profiler indicated, or if a ridge had drifted into the Polynya, they would miss the window, and the mission would fail. 9:03 hours. Sonar reported the U.S. contact had ceased pinging and increased speed. The cruise display showed broadband noise rising, characteristic of a submarine accelerating. The sonar operator offered 2 interpretations. Either the American had lost the track in ice noise and was repositioning, or it had switched to passive guidance and was closing to firing position. The captain asked which was more likely. The operator hesitated, then answered, "Closing to firing position." That meant K-279 had less than 10 minutes before torpedo launch. The captain nodded and said nothing. There was nothing left to say. Around 0906 hours, K-279 reached the Polynya. Ice overhead measured 1.8 meters, within safe margin. Captain Grishkov ordered emergency surface. The crew blew main ballast tanks. High-pressure air roared through piping. The boat tilted upward, accelerating toward the ice ceiling. The sail struck the ice with tremendous force. Estimates suggest as much as 40 tons of impact, shattering the frozen sheet and punching through into open air. The bridge trunk held, no flooding. The periscope mast cleared the surface. The VLF antenna was reeled in. Missile hatches were verified clear of ice debris. And in the radio shack, according to available records, the VLF receiver logged the final block of the launch code. 9:08 hours. VLF code download completed. The communications officer fed the data into the authentication computer, a refrigerator-sized machine in the Radio Shack that cross-checked encryption keys against preset values. Green light, valid code. The crew held their breath. This was it, the moment every submariner trained for, but prayed would never come. The authentication computer had confirmed the message was genuine. But what were the orders? The communications officer read the decoded text. Not a launch order, a drill. A readiness exercise to verify the boat could receive, authenticate, and prepare to launch under operational conditions. No missiles would fire today. The captain acknowledged the drill and ordered the crew to stand down from battle stations. The irony was not lost on anyone. The Cold War ran on the razor's edge between apocalypse and theater, and no one ever knew which was which until the final second. In the Sonar Shack, the operator reported the U.S. attack. Submarine had lost firing solution in the ice clutter and surface noise as K-279's hull acoustics changed during surfacing. The submarine remained surfaced, diesels running in open air where acoustic signature no longer mattered. According to standard procedures for vessels of this class, the generators worked to recharge the batteries, restoring power reserves sufficient for continued patrol operations. The crew secured the diesels, sealed the bridge trunk, and flooded ballast tanks. The boat submerged and set course for the eastern edge of the patrol box, away from the last known position of the U.S. submarine. In his cabin, the captain composed the patrol report. The mission was assessed as a successful test of operational readiness under challenging conditions. He did not mention how close they had come to missing the window. There was no need. Everyone aboard already knew. Post-patrol analysis by Northern Fleet Intelligence. Delta III boats conducted 60 to 80 Bastion patrols per year throughout the 1980s, with only 4 confirmed U.S. trail detections over the entire decade. Success rate an order of magnitude better than the Yankee-class Atlantic patrols, which were trailed 90% of the time. The difference was geography. NATO acoustic surveillance networks in the GI-UK gap could track Soviet submarines leaving port, but under Arctic ice the advantage reversed. The high ambient noise of the shifting ice pack masked acoustic signatures, including machinery noise when the boats operated near the surface, and U.S. attack subs risked collision with pressure ridges if they followed too closely. The Bastion strategy worked not because Soviet submarines were quieter, but because the ice made American submarines louder. The R-29R's 8,300-kilometer range meant Delta boats never had to leave protected waters. That single capability turned the Barents and Okhotsk seas into fortress zones that absorbed dozens of NATO attack submarines in fruitless search patrols. American boats that might have concentrated in Atlantic choke points or Mediterranean flash points were instead tied down hunting for deltas under the ice, where detection probabilities were low and operational risks were high. It was a defensive posture, but operationally, it forced the U.S. to spread its superior submarine force thin instead of massing it where Soviet weaknesses were greatest. Instead of attempting to match American acoustic stealth head-to-head, the Soviets adopted an asymmetric strategy that used geography to negate their technical disadvantages. By 1991, the Soviet Union had built 43 Delta-class boats, though only around 34 remained in active service, carrying over 600 submarine-launched ballistic missiles, a significant portion of the sea-based deterrent. The Bastion strategy remained in place until the end of the Cold War, proving that geography and doctrine could compensate for a technological gap NATO never closed. Today, the Russian Navy still operates 6 Delta IV submarines on Arctic patrols, the last remnants of a strategy born from accepting inferiority and weaponizing the ice. According to some accounts, veteran officers who commanded these patrols witnessed the final years of the era in silence. They never spoke publicly about the missions that tested the limits of endurance and ice. But tradition holds that many patrol reports were filed with the simple summary: mission successful, deterrent maintained, no further details required.